All right, welcome to the Explainer. Today we're going to tackle a question that sounds like it's straight out of science fiction, but it's a very, very real engineering problem right now. How in the world do you program a quantum computer? And here's a hint. The answer has less to do with code and a whole lot more to do with architecture.
So yeah, that's the big question, right? And to even begin to answer it, we've got to shift our mindset. We need to stop thinking like traditional software developers and start thinking a bit more like physicists. Because we're not just typing out lines of code here. We are literally orchestrating the fundamental laws of nature. And any great orchestration, well, it all starts with a master plan.
And that master plan, that's what we call a quantum circuit. So for a minute, just forget everything you know about lines of code. Instead, I want you to picture a super detailed architect's blueprint. That is exactly what a quantum circuit is. It's this precise, step-by-step diagram of every single thing that's going to happen to our quantum data, from the very start to the very finish.
So here's how we're going to break it all down. We'll start with the blueprint itself. Then we'll look at the tools of the trade, the bits and the gates. After that, we'll see how you can assemble small designs into much bigger ones. Then comes the fun part, taking that blueprint into the real world. We'll explore the hurdles of today's hardware, and finally, we'll talk about why the future of all this is completely open source. Okay, let's dive in. First up, the quantum blueprint. Every design has to have a solid foundation, right? Well, in the world of quantum programming, especially when you're using tools like Qiskit, which is a big open source software kit, that foundation is something called the quantum circuit. Just think of it like the master file, the container that's going to hold and organize every single piece of our design. And any good blueprint has to start by listing the materials. For us, that means we need to define two core components. First, you've got the quantum bits, or qubits. These are the things that do all the heavy lifting, the actual quantum computation. But then you also need classical bits, the good old ones and zeros. And their job is to store the final answer once we measure the qubits. Because at the end of the day, all this fancy quantum stuff has to spit out a classical result that we can actually read and understand.
All right, so we've got our foundational blueprint. Now it's time to actually start drafting, which brings us to our raw materials and precision tools, the bits and gates.
The big idea here is really just organization. Our basic building blocks are the qubits and the classical bits. But, when designs get complicated, we need a way to keep things tidy. So we group them into what are called registers. A quantum register is kind of like giving a name to a specific team of qubits, and a classical register is like the designated spot where they'll file their final reports. It's all about making that blueprint easy to read and manage.
Now, this is a really important distinction to make in our toolkit. You have instructions and you have gates. An instruction is pretty much any action you can take, like measuring a qubit to get a result. But a gate is special. It's a precision tool. And the number one thing that makes it special is that it has to be reversible. You have to be able to run it backwards and get back to where you started. And this isn't just some nerdy technicality. It's absolutely essential. Reversibility is what preserves the delicate quantum information while the computation is happening. If an operation isn't reversible, it's not a true quantum gate, period.
So how do we make these blueprints more flexible and powerful? Well, we use something called parameters. Think about it. Instead of permanently setting the angle for every single rotation gate, what if we left it as an adjustable knob? That's what a parameter is. It means we can create one master blueprint and then just tweak the knobs for different tasks. It's way, way more efficient than having to design a brand new circuit from scratch every single time.
Okay, on to our next section, assembling modular designs. Nobody builds a skyscraper by designing every last nut and bolt from scratch, right? Of course not. They use prefabricated, standardized modules. And it turns out, quantum programming works exactly the same way. We build really complex algorithms by snapping together smaller, proven circuit components.
The main tool we use for this is the compose method, and it's pretty much exactly what it sounds like. You design these small subcircuits that each do one specific job really well, and then you compose them, you combine them to build something way more powerful. And what's really cool is you can even wrap up that new combination so it just looks like one single block on your main blueprint. It's a fantastic way to manage complexity.
And here's the best part. You don't have to build all of these modules yourself. The Qiskit Circuit Library is basically a professional toolkit that's already jam-packed with pre-built, highly optimized modules. So let's say you need a common algorithm, like the quantum Fourier transform. Yep, it's in there. Or maybe you want to test how well a quantum computer is performing with a special benchmarking circuit. It's ready to go. This kind of standardization is absolutely key for the whole field to move forward, quickly and reliably.
All right, so we've got our blueprint all designed. Now for the moment of truth, actually running it and getting a result back. And to do that, we need a standardized way to talk to the hardware. These special interfaces are called primitives. You can think of them as the bridge connecting our perfect abstract blueprint to the real physical quantum computer.
And there are two main types of these primitives. First, you've got the sampler. Its job is to run your circuit, measure the result, and then do that over and over again, maybe thousands of times, to build up a probability distribution of all the possible outcomes. It's perfect when you're trying to find the most likely answer to a problem. Then you have the estimator, and it's a bit different. Its goal is to calculate a specific value, like the energy of a molecule in a chemistry simulation. And here's the really crucial rule. An estimator circuit absolutely cannot have any measurements inside it. Why? Because the very act of measuring would collapse the quantum state and destroy the exact information you're trying to analyze.
It also really matters how you send your blueprint to the quantum computer. If you just have one quick experiment, you can submit a single job. Simple enough, but what if you have a whole bunch of different independent circuits you need to run? That's where batch mode comes in. It processes them all in parallel and saves you a ton of time. And then there's session mode. This is like renting out the entire machine for yourself. It gives you dedicated, low-latency access, which is absolutely vital for those complex, iterative algorithms where the result of one run immediately determines what you do in the next.
And this is where we get a bit of a harsh reality check. So far, everything we've talked about has been perfect, on paper. But what happens when our elegant, beautiful blueprint meets the messy, noisy, and imperfect reality of today's quantum hardware? Well, that's where the real challenge begins.
You see, our single biggest enemy is, and always has been, time. Quantum states are just incredibly fragile. They only exist for these tiny, tiny fractions of a second before they fall apart. They lose all their precious quantum information. This process is called decoherence. So a circuit's depth is basically just how long it takes to run from start to finish. And that means the number one job for any quantum architect right now is to design the absolute shallowest, fastest, most efficient circuit possible. It's a constant race against the clock to get your answer before the quantum state literally vanishes into thin air.
And to really understand the scale of this error problem, just consider this number. To protect just a single piece of quantum information from all that noise, we have to build something called a logical qubit, using some very clever error correction. Well, the current estimate is that building just one of those stable, logical qubits is going to require thousands of the noisy, physical qubits we actually have today. I mean, the overhead is it's immense. And then there's this other, often underestimated bottleneck. See, most of the problems we want to solve start with a bunch of classical data. But it turns out just the process of loading that classical data into a quantum state can be so incredibly slow that it completely wipes out any potential speedup you were hoping to get from the quantum computer. It's a huge problem.
So, with all these massive challenges, how on earth do we move forward? Well, that brings us to our final section. The future is open source. The truth is, the complexity here is just too great for any one company or any one research group to solve on their own. The entire field absolutely depends on a collaborative, transparent, and open source approach.
And for that to work, the community really needs a clear set of rules. We're talking about everything from inclusive, accessible software licenses to fostering active community feedback and, of course, implementing really robust, peer-reviewed security measures. This framework for collaboration, it's honestly just as critical as the physical hardware itself. It's all about building the trust and the transparency we need to make sure this incredibly powerful technology develops in a way that's safe and beneficial for everyone.
And that really just leaves us with one final thought. We've just walked through how we construct these quantum blueprints, right? From the simplest components all the way up to complex designs. So the real question is, as these simple sketches start to evolve into the equivalent of sprawling city plans, what are the currently unsolvable problems that we're finally going to build solutions for first? Will it be discovering new medicines, designing revolutionary new materials? It's that potential. That's what makes this entire field so unbelievably exciting. Thanks for joining me on The Explainer.